Hello, today we'll look at Newton's method. This is a numerical method or numerical algorithm for solving nonlinear equations. Newton's method is extremely popular due to its simplicity and high accuracy. And our focus today is applying Newton's method to solve system of nonlinear equations. And then we'll look at its main idea and some examples. So suppose you have a vector function f of x. So f is a function from Rn to Rn. So the equation reads f of x equals to 0. Okay? We assume the system has a solution. This will be our assumption from now on. And also we assume that f of x is continuously differentiable. That means all the first order partial derivatives of f exist and are all continuous. In general, such system of equation does not have a closed form solution. So some kind of approximate method has to be used. And these are the steps for Newton's method. So first we're going to solve a system of linear equations, which is much simpler. This df of xm minus 1 is a matrix. Delta xn is an unknown vector. So the first step in the Newton's method is to always solve a linear equation. And then we update xm minus 1 to xn by adding this delta xn to xm minus 1. And then we just repeat this process until the method quote-unquote converge. Basically means the xn doesn't change so much. Okay, and of course, to get this iteration scheme running, we need an initial condition. So when n is equal to 1, this method calls for x0. x0 is the initial condition. So that's the method. However, I have not explained what this df symbol means, and we shall take a look at that real soon. But before we study system of equations, let's just first review Newton's method for a scalar equation, f of x equals to 0. So f of x here is a scalar function. It takes a real number as an input and returns a real number as output. The Newton's method for scalar equation is a standard application of differential calculus. It says, starting with the initial guess x0, xn for n equals to 1, 2, 3, and so on are computed iteratively. According to this formula, xn equals to xm minus 1 minus f of xm minus 1 divided by f prime of xm minus 1. F prime stands for the derivative of the function f of x. So obviously we need f to be differentiable for this method to make sense. And here's a fact. If the initial guess is close to the exact solution, once again we assume the exact solution exists, then the sequence x0, x1, x2, and so on converges rapidly to the exact solution. So when Newton's method works, it works very, very well. Let's look at the main idea of Newton's method, which is linearization. And really, that's the same idea that works for both the scalar case and the system case. So for now, let's still stick to the scalar case. We know that at the initial guess, x0, f of x can be linearized. That is, f of x is approximately f of x0 plus f prime of x0 times x minus x0. Geometrically, the right-hand side is really the equation of the tangent line of the graph of f of x at the point x0, fx0. We'll see a geometric illustration very soon. So now f of x is approximated locally as a linear function. So f of x can be highly nonlinear, so solving f of x equals to 0 can be hard. However, solving the linear equation is always easy, relatively speaking, so to say. So that's why we work on this simplified task, that is, setting the right-hand side to 0 and get a linear equation in x. So now it is just a matter to solve for x, which is quite easy. By rearranging, we get f prime of x0 times x minus x0 equals to minus f of x0. X minus x0 is then the minus of f of x0 over f prime of x0. And finally isolate x, we get x is equal to x0 minus f of x0 over f prime of x0. So notice that this is exactly the x1 in Newton's method. So now we can just repeat this process. You replace all the x0 on the right hand side by x1, and you get the new iteration, which is x2. And that's exactly Newton's method. So the idea of Newton's method is to locally linearize the function and then solve a linear equation. And we do that iteratively, and hopefully the sequence produced by this iteration process will converge to the exact solution with arbitrary precision. And now let's look at a geometric interpretation of the algebra we just did. So here we have a nonlinear function f of x, and here's the x star on the x-axis. That is the exact solution of f of x equals to 0. But now suppose we pick an initial guess, x0. If x0 just happens to be the exact solution, then we're done. But this is almost never the case in practice. So what do? We pick a point on the graph of f of x, whose x-coordinate is x0, and at that point, we draw a tangent line of the graph, which is this blue solid line. And the point where the tangent line intersects the x-axis is what we call x1. Because remember, x1 is the solution to the linear equation. So as we can see, x1 is a better approximation than x0 to the exact solution x star. At least that's what the graph suggests. Well, whether that's true in every situation is debatable. And after that, we just need to repeat the same process. Pick the point on the graph of f of x, whose x-coordinate is x1, and then draw a tangent line from there. The new tangent line, which is the red solid line, intersects the x-axis at x2. And that's the next approximation. So hopefully by repeating this process over and over again, we can get a very good approximation to x star. For a concrete application, let's consider approximating square roots. In fact, this method is called Heron's method. It was discovered way before Newton's time. So to approximate the square root of a, where a is a positive number, is to solve the equation f of x, which is defined to be x squared minus a equals to 0. Let's see what the Newton's method looks like for this particular function f of x. So first we calculate the derivative, which is 2x. That's very easy. And then we just plug in the general formula for Newton's method. So xn equals to xn minus 1 minus f of xn minus 1 over f prime of xn minus 1. F of xn minus 1 is xn minus 1 squared minus a. F prime of xn minus 1 is just 2xn minus 1. Simplifying the fractions, and we get xn is 1/2 times xn minus 1 plus a over xn minus 1 quantity. I made a separate video on Heron's method a long time ago. And the iteration formula here we just derived also have an intuitive meaning. So let's say xn minus 1 is the current approximation to the square root of a. Xn minus 1 may be smaller or greater than the exact square root. If xn minus 1 is an underestimate, then a over xn minus 1 has to be an overestimate, and vice versa. So what this formula does is we take an average between the underestimate and the overestimate. And in my old video on Heron's method, I actually proved this sequence converge. Link in the video description. And here's a quick example to approximate the square root of 2 with x0 equals to 1. The red digits are the correct digits. And now let's turn our attention to a multivariable setting. Let's consider a system of equations of this form. We have f of x y equals to 0 and g of x y equals to 0, where f and g are scalar valued, continuously differentiable functions. Here we use a bivariate setting. That means we have two unknowns and two equations. The idea can be easily generalized to situations with n unknowns. And once again, the overarching idea is still linear approximation. Let x0, y0 be the initial guess. F of xy is approximately equal to f of x0, y0 plus first order partial derivative of f with respect to x evaluated at the point x0, y0 times x minus x0 plus the first order partial derivative of f with respect to y, once again evaluated at x0, y0, times y minus y0. And here, the right-hand side, instead of just having one derivative compared to the scalar case, we have two partial derivatives. And the right-hand side is, in fact, the equation of the tangent plane to the graph of the function fxy. And also we have a linear approximation of g near the point x0, y0. So what we're going to do next is to simply set the right-hand side of these two approximations to be 0 simultaneously. And that gives us a linear system of equations in x minus x0 and y minus y0. We can then write the linear equations in matrix form. And doing this is almost a second nature to any applied mathematician, because matrices are so much easier to work with. So from here to here, we move the constant terms to the right-hand side. And then we have a 2x2 matrix that is df dx, df dy, dg dx, and dg dy, all evaluated at x0, y0, times the difference vector, so to say, x minus x0, y minus y0, equals to minus f and g evaluated at x0, y0. So this is the matrix form. To make things more compact, let's give names to the matrix and the vectors. So here are the vector matrix notations. The bold x is a vector that has component x and y. The vector function f of x has two components, f of xy and g of xy. And also we have the vector xn. The Jacobian matrix df of x, this is a 2x2 matrix valued function of the vector x. And then we can rewrite the derivations we did earlier in matrix form. So nothing will be new here, but it just makes things more compact. And this is the derivation we just did. First, we make a linear approximation of the nonlinear function f of x. So that's f of x is approximately f of x0 plus d of x0 times x minus x0. The linear term I'm highlighting right now is a vector matrix multiplication. And then we set the right-hand side to be 0. This is a linear equation, or shall we say linear system of equation, in the difference vector x minus x0. So x minus x0 can be symbolically represented as minus the inverse matrix of df x0 times f of x0. And lastly, separating x, and we get x0 minus df of x0 inverse times f of x0. So as you can see, this looks very similar to the scalar version of the Newton's method. In the scalar version, you have f of x0 divided by the derivative. But here, because the derivative is no longer a scalar, its place is now occupied by the inverse matrix of the Jacobian, which plays the role of the reciprocal of derivative in the scalar case. The right-hand side now will be called x1, and then we can just apply this procedure over and over to get x2 and x3 and so on. So now we finally have the Newton's method for a system of equations fx equals to 0. In our derivation, we use the inverse matrix symbol. However, for numerical computations, unless the Jacobian matrix has a very small size, let's say 2x2 or 3x3, we do not want to reference inverse matrix directly in the algorithm, because inverting a matrix is typically quite an expensive operation, and usually there are better ways to solve linear systems than directly computing the inverse. So that's why in our method we say first we solve the linear system, df times delta x equals to minus f. Mathematically, this is equivalent to inverting the Jacobian. The delta xn we just solved can be seen as an increment, and the new xn will just be the old xn plus this increment, and that's our update. And we'll do this iteration until the increment size is small enough, and that's our convergence criteria. There are other convergence criteria. For example, you can plug in xn into f, right? If xn is close to the exact solution, then f of xn must be very small. That's another way to decide when to stop the algorithm. This absolute value sign stands for some kind of norm. And for example, we can use Euclidean length. But other norms can also be used. For example, the maximum norm and so on. It doesn't really matter. So now let's look at an example. We have a system of nonlinear equations. X cubed plus y equals to 1 and y cubed minus x equals to minus 1. I use this example because it has an obvious solution. Here I am in Desmos. I plotted the two equations in the system. Each represents a curve on the xy plane. And as we can see, they have an intersection which just happens to be a 1, 0. And we can also verify x equals to 1 and y equals to 0 is indeed a solution. In fact, that's the only solution. So we choose this simple example because it has an exact solution, and we'll compare the performance of Newton's method with that exact solution. So now let's apply Newton's method. With initial guess, x0 equals to 0, 0. I just randomly pick initial condition. Feel free to use other initial guesses to practice your understanding. Let's begin by rewriting the system in matrix form. So we want the system to be in the form f of x equals to 0. And f of x is a vector function with two components, f and g. F of xy is x cubed plus y minus 1. And gxy is minus x plus y cubed plus 1. So now we have the vector function f. Let's calculate its Jacobian. This is very straightforward. All the partial derivatives are easy to obtain. df dx is 3x squared. df dy is 1. dg dx is minus 1. dg dy is 3y squared. And we get dfx is 3x squared, 1 minus 1, 3y squared. So I computed 6 iterations on a computer. This might look a little bit overwhelming, but I will do the first 2 iterations by hand to illustrate what is going on. Here we go. I'm on Paint right now. We have the vector function f of x and its Jacobian. Let's start with the first iteration. The initial guess, x0 is 0, 0. We get f of x0 is equal to minus 1 and 1. Then we plug in 0, 0 into the Jacobian, and we get 0, 1, minus 1, 0. So now we need to solve a system. df of x0 times delta x is the unknown, is equal to minus fx0. Therefore, delta x can be written as the inverse matrix of 0, 1, minus 1, 0, times minus fx0, which is 1 minus 1. And because this is a 2 by 2 matrix, its inverse is very easy to find. I'm putting the 2 by 2 inverse matrix formula on the side for convenience. And to carry out this algebra, we have the inverse is equal to 1 over the determinant, which is 1, times 0, minus 1, 1, 0. And then times 1 minus 1. Do the matrix multiplication. 0 times 1 plus minus 1 times minus 1 is 1. x1 is x0 plus delta x. x0 is 0, 0. Delta x is 1, 1 that we just found. And that means x1 is 1, 1. So that's the first iteration done. Okay, so let's go back to our table and see the results. So we have n is equal to 1. The initial guess, that is x0, 0, 0. And this is the function value, the Jacobian value, the Newton step, the difference delta x is 1, 1, and the update is 1, 1. And finally, we give the size of the step because we need this to determine whether we stop the algorithm. Okay, so now let's move on to the second iteration. Now we compute the second iteration by hand. That is to calculate x2 from x1 from the first iteration. Evaluating fx1 and dfx1 gives us minus 1 and 1 and 3, 1, minus 1, 3. So then we calculate the delta x, which is the inverse of 3, 1, minus 1, 3 times minus 1, 1, which simplifies to minus 0.2 and minus 0.4. So x2 is x1 plus delta x, which is 1, 1, plus minus 0.2, minus 0.4, which is 0.8 and 0.6. And that's the end of the second iteration. If we look at our table, that's exactly the result we obtained from the second iteration. And we just do this process over and over again, and at the sixth iteration, the result is extremely close to the exact solution 1, 0. And here's a graphical visualization. I started from 0, 0. The first iteration gives us 1, 1. And the second iteration is 0.8, 0.6. And it just goes closer and closer to the exact solution 1, 0. And that's the end of today's video. Newton's method is extremely powerful, and there's no doubt in future we'll see some applications of Newton's method in concrete engineering problems. Thanks very much for watching, and I'll see you next time. Bye.